Hello students, welcome to another video on rigid body rotation. In this video, we observe the application of angular momentum and its conservation. So the formulas are pretty much similar to the ones you saw when you are dealing with linear momentum. The only difference is, of course, would be the fact that in circular motion, we use the moment of inertia instead of the mass, and we use angular velocity instead of the linear velocity we used in the conservation of momentum. So I hope you had time to go through the question. I hope you tried it and you were able to find something. So let's try to see what you found. And for those who were not able to try it out, just say you can try to pause the video and try to work out the question. Okay, so we can dive right in. So here we're talking about a merry-go-round that is made of a uniform solid disk. So what that is just telling us is we have to take into account the moment of inertia of the disk. And for a solid disk, I hope you guys know to say the moment of inertia is given by half the mass of the disk times the radius squared. Okay, so apart from that, they're saying it is rotating at a velocity. So that is an angular velocity, 15 revolutions per minute. Now, about the vertical axis. The radius of the disk is, that's 6 meters. We're given the radius as well. That is 6 meters. The mass was given earlier. That was 150 kgs. So already with what we're given, we're able to get the moment of inertia. So now they say, if an 80 kg person quickly sits down on the edge, what is its new angular speed? So they want the new angular speed of the merry-go-round, which was initially moving at 15 revolutions per minute, after the person whose mass is 80 kg sits on the edge of the same merry-go-round. Okay. Now, I'd like to relate this to linear momentum so that you guys can easily relate to these concepts. If you are still having challenges with linear momentum, or maybe you haven't seen the area practice questions we worked out on linear momentum, I'll put a link in the description so that you can just quickly try to check out that topic as well. Okay, so from linear momentum, what we saw, its conservation, we had if two objects are going to interact, so we would have the mass of the first one multiplying the velocity of the first one of the same object initial, summing to the mass of the second one times its velocity before collision, being the same as the mass of A, the velocity of A after collision, plus the mass of B, the velocity of B after collision. So this was from linear momentum. Now what we're saying is, in terms of angular motion or circular motion, we use moment of inertia for mass, and we use angular velocity for velocity, for V. So this expression now looks something like this. Okay. So I hope you guys were able to relate to this. So I'm taking this approach so that it's easy for you guys to remember, assuming that you actually understood the earlier topic of linear motion or linear momentum. So that is of B, angular velocity final of B. Now, after taking note of this, you see, the question is saying the merry-go-round is rotating. So the merry-go-round has an initial velocity, angular velocity. But the person was, let's assume the person was just standing next to the merry-go-round. The person was not moving. So the assumption here, since the question does not say anything about it, the assumption is that the person was initially not moving. So the angular velocity of the person was 0 initially. So the left-hand side now just remains as the angular the moment of inertia of the first person of the merry-go-round, the angular velocity of the merry-go-round before. This is equal to the moment of inertia of the merry-go-round, the angular velocity after collision of the merry-go-round, plus the moment of inertia of the man, the angular velocity of the man after collision. Now, this is how our equation now looks like. The next thing that we have to look at is the man sits on the merry-go-round. So what happens is they'll have the same velocity after collision. The collision here is that's the part where the man sits on the merry-go-round. So saying after collision, the angular velocity of the merry-go-round is going to be equal to the angular velocity of the man. So let's just use angular velocity final for that. So if we write our equation, now it becomes the moment of inertia of the merry-go-round, the angular velocity of the merry-go-round before collision equal to the moment of inertia of the merry-go-round, the angular velocity of the merry-go-round. So now we're just using final since it's the same. So angular velocity final plus angular velocity for, moment of inertia for the man times the angular velocity after collision. Now we can easily factor out the angular velocity final. So now we remain with angular velocity for the merry-go-round, moment of inertia for the merry-go-round, moment of inertia for the man, and then we have angular velocity after collision outside. So from here, we can then make angular velocity final the subject of the formula, since that's the one we want to find. So we divide both sides by moment of inertia A plus moment of inertia B. So this now becomes moment of inertia A divided by moment of inertia A plus moment of inertia B. This is multiplying the angular velocity initial of the merry-go-round. This is what gives us the final velocity, angular velocity after collision. Now, here all we need to do is just calculate the moment of inertia for the merry-go-round. So we're saying omega A, our moment of inertia A, this is for the merry-go-round. So this is for the merry-go-round. And then moment of inertia B, this is the moment of inertia for the man. Now, how do we get that? So the merry-go-round is made out of a disk according to the question. So the moment of inertia for a disk is given by half mr squared. So from here, this becomes half. The mass of the disk is given to us, and this is given as 150 kgs. The radius of the disk is given as 6 meters, so it has to be squared. So if we work this one out, we're going to get 2,700. So 2,700 kgs meter squared. And then now for the man, you see, we in this case, we have to take the man as if he was a point object. So the idea is we treat this person as just a point particle that is on a disk of radius 6 meters rotating about this point. So basically what we have is just more like an object that is rotating in a circular path. So the moment of inertia for such a system is given by mr squared. So notice that this is this is basically just a format that we use to derive the expression for torque in the introduction video. So from here, since we're saying this gives us the moment of inertia for the man, so we're saying IB for the man, it's mr squared. This will now be equal to the mass of the man. That's 80 kgs multiplying the radius. That's not 60, that's 6 squared. So if we work this one out, we're going to get 2,880 kgs meter squared. Now, having obtained the moments of inertia for both the merry-go-round and the man, the next part now is just the substitution. So we're already given what the angular velocity is. So this is omega final is equals to IA over IA plus IB multiplying angular velocity for A initial. Now, the moment of inertia for the merry-go-round, we did find it, that was 2,700. And then the moment of it's the same thing here, same value, plus, and then this is 2880. So now we have an option here. So we notice that these will have the same units. So the kg meter squared will cancel from these values, but they multiply the angular velocity. So whatever the units of this, that will be the unit of our final answer. Now, this currently is given to us in revolutions per minute. So we have a choice here. Depending on what the question will be for you guys, depending on what the question is, you either have to convert it to radians per second, or you can leave it in that format. In this case, you can still use it the way it is. So you can use it as 15 revolutions per minute. And then if you did that, the answer you get is going to be 7.26 revolutions per minute. But if your question is asking you to get the answer in radians per second, then you can quickly just convert this to radians per second. I know you guys are capable of doing that by now, but just in case you want me to show you, we can quickly do that. So that's 7.26 revolutions per minute. And then here, again, as always, this is just going to be times 2 pi. And then after this is going to be times 1 minute over the 60 seconds. So this cancels with this cancels with that. And you get 0.760 radians per second. Okay. All right, you guys, I think that's all the time we have for this video. Hope you found it helpful. So there are many questions which can be phrased in terms of these topics. You guys just have to understand what is happening. So in the next question, for example, I'd like you guys to just try it out. So yeah, just try to go through the question, understand what they're asking you to find, and then try it out. And if you do struggle, you don't know which approach to take, you can check in the comment section. I will leave a comment there with the main concept that you're supposed to use. And yeah, I hope you'll be able to work it out. Okay, so I think that's all the time we have. And if you guys have any other questions that you want me to work out for you and make a video out of there, you guys can just yeah, send the questions to me using the email in the description. Otherwise, hope you found this helpful. All the best.